Okay, I think we can start. Good afternoon, ladies and gentlemen. We continue our series of Moscow Sommunications seminars, and today we will have a very exciting talk, which will be given by Dr. Nikola Zlatanov from Australia. Dr. Nikola Zlatanov is a senior lecturer in the Department of Electrical and Computer Systems Engineering at Monash University in Melbourne, Australia. His current research interests include wireless communication, information theory, and machine learning. And he received many scholarship and best paper awards, and currently he's an editor of IEEE Wireless Communication Letters. So because of very broad research interests of Dr. Zlatanov, the talk will be, I hope the talk will be very interesting, and the talk is applications of the communication theory framework to machine learning and to blockchain. So the floor is yours, please.
Thank you. Thank you for inviting me to give this talk. So I'll share my screen and then I'll stop the video, my video. It will be just the screen. So this talk will be divided into two parts. The main part is machine learning as a communications theory problem. This is will be basically 90% of the talk, and at the end I will just give a blockchain problem and how we can model that blockchain problem with communications theory. So the second part is just the work in progress. So we start with the first part, machine learning as a communications theory problem. And this work is based on two papers. So the first is a technical paper, and both are submitted papers. So the first is with my PhD student Farzad, and the second is a tutorial paper in Wireless Communication magazine. So the talk will be basically also a combination of more as a tutorial, and also there will be a technical part, but it will be very simplified. So I won't get into details of the technical paper. I won't get into proofs. Okay, so first, the importance of machine learning. We all know how important machine learning is. I mean, it's everywhere. And without any exaggeration, we can say that definitely it is the most impactful research discipline in the last decade, and maybe a little bit more. It's so impactful that the general public has started to ask if artificial intelligence will surpass human intelligence in the near future. And all branches of academia have tried to employ machine learning algorithms to improve their algorithms or to solve some of their open problems. And definitely wireless communication is not an exception. So machine learning in wireless communications is one of the main hot topics now in wireless communications, and everyone is trying, not everyone, but there's a lot of researchers trying to employ machine learning to improve the existing wireless communication schemes. Okay, so a little bit about the history of machine learning. So the history in terms of the research directions or the inspiration for machine learning. So machine learning has been mainly inspired by the workings of the human brain, and this inspiration has a long history, and we can say that maybe it starts with this paper in which gives a computational model for the neural networks, and a paper who recently sparked the research interest in machine learning is this paper too, where the authors showed or developed a neural network that recognizes images and that at the given time had superior performance with the other algorithms for image recognition. So what I will argue in this talk is, instead of machine learning inspired by the human brain, we take a look at whether we can develop machine learning from communications, in communications inspired machine learning. So this I will do by looking at the machine learning problem from a new perspective, from the perspective of communications theory. And I will show that the two main machine learning problems, supervised classification and unsupervised classification, can be represented equivalently as two simple communications theory problems. So simple in the sense of they can be represented simply as problems, but not simple in the sense that they can be solved easily. So machine learning has two main problems: supervised classification, unsupervised classification, and reinforcement learning. So I will talk only about classification. So why is this representation important? It is important from, at least from my point of view, from the field that I come from communications, from the communications community, is to enable researchers to see, researchers from the fields of communication information theory, to see the machine learning problem as a familiar problem that they have worked on, at least in part or approximately, in their prior research. And this will allow a vast body of knowledge and intuition from communication information theory to be applied to machine learning, because those researchers will find the machine learning problems as familiar problems, and then they can tackle some of the open problems in machine learning. So in fact, I argue that because of this equivalent representation of classification and maybe of reinforcement learning, it can be concluded that the researchers from the fields of communications information theory are one of the best suited for tackling some of the open problems in machine learning. So what are the open problems in machine learning? Which problems can we try to tackle? One of the main problems is the lack of tight theoretical guarantees on the performance of the different proposed machine learning algorithms. So for example, usually when a machine learning algorithm is proposed to solve a given problem, then we cannot be sure a priori what will be the performance of that algorithm. Now, and in fact, how one arrives at a good machine learning problem for a given, good machine learning algorithm for a given problem is in part by employing the trial and error approach. So there is here there is in a part that is art, that is how using the trial and error approach to get to a good machine learning algorithm. And there's a famous talk by a famous machine learning researcher who has compared, because of that, has compared the designing of machine learning algorithms to alchemy. So this is in contrast, at least to communications engineering, where we in communication engineering, the algorithms that we provide, they all come with theoretical guarantees on their performance. So if those algorithms, they are implemented in practice, there are some theoretical guarantees that those algorithms will satisfy. These theoretical guarantees are expressed in the form of bit error rates, data rates, outage probabilities, etc. So this is what we will try to do. Can we also provide theoretical guarantees for the classification problem? So let's model the classification problem. So the classification problem can be modeled as in this figure. There's a classifier. The classifier has an input and an output. The input is yn of x. Yn of x is a vector from y1 to yn that represents the features. So it's a feature vector. It has length n, and it's a function of x, meaning that it is mapped to the label x. Okay, and then the aim of the classifier is looking at the feature vector yn. It wants to learn what the label x is. Now, instead of label x, the classifier gives an output label x hat, just because sometimes it makes a mistake. Okay, so we can imagine this here, yn of x, as the image, let's say, of a cat, and x is the cat, or the word cat. And x hat, as I said, is the learned label. And the aim of the classifier would be to minimize the error rate, so the probability that the detected label is different than the actual label. Okay, so now let's model the dependency between the label x and the feature vector. The more general way of how the dependency between the label x and yn can be given is by a joint probability distribution. This is the joint probability distribution between x and y of n. And now I would like to include this joint probability distribution into this model, just to be more clear. And so first I represent this joint probability distribution as a conditional distribution times the marginal. So because this holds, this equality holds, instead of the joint distribution, instead of including the joint distribution directly into this model, I can introduce the conditional distribution and also this distribution. Okay, so then what would P of x represent here? It would represent the frequency at which different labels come or appear for classification. So that's why P of x can be modeled by a source. And what the conditional distribution represents the transformation that the label x undergoes before appearing as a feature vector at the input of the classifier. So as a result, it can be modeled as a communication channel. So I can represent this equivalently, this classification model as follows. I have a source. The source generates labels x. The source generates the labels x according to this distribution, P of x. Then the label goes into a channel, or in this case, we can think of it as some kind of a feature generator, right? As input, this feature generator has the label, and as output, it produces the feature vector. Then the classifier has as input the feature vector and wants to detect what x is. And instead of x, it outputs x hat. Now let's compare this model with the communications model. In the communications model, we have the following, right? We have a source encoder, we have a channel decoder. The source produces, in this case, some message x. This message x is encoded, so it is transformed into a vector. In this case, I denote by x bar of k, so it's with length k. Then this vector here goes through a channel modeled by this conditional distribution. At the output, there's another vector, yn of x, and there's a decoder. The decoder looks at yn and wants to detect what x is, and the decoder outputs x hat, and the aim is to minimize the error rate, so similar as in the classification problem. So definitely, when we compare the two, definitely the classification problem is a special case of the general communication model. So what is missing here is the encoder. So what this means is that in the classification problem, we cannot somehow optimize the transmit side of the problem. So we can only optimize the receive side of the model, which is the classifier, or in this case, the decoder. So what comes into the channel is out of our reach. X goes into the channel, and we cannot change x. We cannot change the distribution of x. We cannot change the values of x. So what we can only change is the classifier, because the encoder is missing. Okay, so now another property is that the x that goes into the channel, or the feature generator, is a one-dimensional variable, and yn is a vector. Okay, so we can represent this model more accurately or more intuitively as this model, right? Now, this is the final model. There's a label x going into a channel. The channel produces n outputs. All these n outputs go into the classifier, and looking at those n outputs, the classifier wants to figure out what x is. And as you can see, this is, in communications theory, this is the single input, multiple output channel. Okay, so now let's see what is training in machine learning from a communications theory perspective, right? So in training, there's a known input x. The label is set to a fixed value, x small, and then t outcomes of the feature vector are observed, and then they are stored at the classifier as site information, with the note that these outcomes of the feature vector, they all come when the input was set to small x. Okay, so there is something similar in communications, right? There is what is called training, or pilot training, and it is used for estimating the channel. And why do we do that? Is because when we estimate this channel, then the optimal detector, or in this case, classifier, is known. It's the maximum a posteriori classifier. However, in real-world machine learning problems, this conditional distribution is first extremely complicated compared to the distributions or the channels found in communications problem. And secondly, it cannot be estimated perfectly. It can only be estimated perfectly when t goes to infinity. but usually, I mean, most certainly, t doesn't go to infinity, but there is this drive for more and more training data that is heard, I mean, all over the literature, and we can think of why there's a need for such drive is because if we have more training data, we can estimate this channel more perfectly, and then we can then get we can have the optimal classifier. But definitely this conditional distribution or this channel cannot be estimated perfectly. In fact, it's very poorly estimated, and this is the main problem of classification. So classification in machine learning, we have a communication through a channel, which is very, very complicated, highly dimensional, and it is very poorly estimated. So how can we make a classifier which can detect what is the input to the channel when that channel is very poorly estimated and very complicated? So especially the problem is even more emphasized because this vector here, which is at the output of the channel, it is comprised of elements which are mutually dependent and non-identically distributed. So here, this distribution is unknown, and this distribution produces elements which are mutually dependent and non-identically distributed. And we, as a research community, have had difficulties in coming up with a framework for deriving tractable or closed form expressions when we analyze random vectors with dependent and non-identically distributed elements, especially when we don't know from which distributions those elements come from. And this is, again, the problem in machine learning. And that's why, because of this representation, right, because of this dependency and the unknown conditional distribution, we cannot get into closed form solution. We cannot derive tight upper bounds on the performance of classification. So how can we go around this problem? We can go around, I believe we can go around this problem with independent component analysis. So independent component analysis is a class of algorithms that take as input vectors with dependent, non-identically distributed elements and produces outputs vectors with independent elements. They do not necessarily will be identically distributed, but they will be independent. And that transformation is irreversible. So it is therefore, I mean, not in all cases, but it is either with zero or very small loss of information. In fact, this paper, it's the first paper that proposed ICA algorithms that perform this transformation from vectors with dependent elements into vectors with independent elements for general nonlinear mixtures and without any loss of information. So because of that, because there's no loss of information, because there exists such a transformation, and that transformation, the complexity is exponential. So the more elements the vectors have, the harder it is to obtain such a transformation, but it exists. And because it exists, we can now replace this model equivalently with this model. In this model, we have an input X, a label that comes into n different channels. These n different channels now produce features which are now independent. Okay, so the entire channel in machine learning now can be represented as a product of these channels, n channels, where these n channels don't have to be identically distributed. They can be either equal, I mean, they can be identically distributed or non-identically distributed. So meaning these features here that the classifier sees, they are independent, but they don't have to come from the same distribution. They can come from different types of distribution. And why independent features is much better than dependent features? Because each feature now provides a independent information. In the case when these features, they come from the distribution which produces dependent elements, then in part each feature carries information which other features also carry, right? The mutual information between y1 and y2 is definitely not zero, which means that the information, there is information in y1 that is contained also in y2. And this is something that is not needed. I mean, what the classifier needs is when he obtains the information from y1, he doesn't need to obtain that information again from the feature y2. For the classifier, it is best if the feature y2 now describes something totally independent what feature y1 described. And intuitively, the more independent features we have, the more accurate the classifier should be. Why? Because if we have a label which can be described, let's say n is infinite with infinitely many descriptions, where each description is totally independent from all others, definitely that classifier would not make a mistake. So I will also talk about this in the following. Okay, so this is, until here is the tutorial part of the paper. So this is basically the magazine part of the talk. Now I will talk about I will represent the technical paper, okay? So I will represent an asymptotically optimal classifier when the feature vector has, this is incorrect, when the feature vector has independent and non-identically distributed elements. So I will present a classifier, an asymptotically optimal classifier for this problem, when the features are independent. Okay, so let X calligraphic contain all possible labels X. Let's assume that the classifier has T small training feature vector for each label that is in X. Okay, and then let this here, Py hat NT, denote the estimation of the channel from the label I from the T feature vectors. Okay, and now the classifier receives this outcome from Yn, so Yn small, and it's the observed feature vector whose label the classifier wants to detect. And let's assume that the classifier makes an empirical distribution of Yn, okay, and denotes it like this, P of Yn. And then we have proposed the following classifier. It is basically the classifier decides for the label Xi, which is closest in terms of, this is Minkowski distance, which is closest in terms of distributions estimated distributions from the empirical distribution made for the ith label. Okay, so if the distribution that we receive yn, based on yn, we make this distribution. So if this distribution is closest to the distribution of the channel based on the ith label, we decide that the ith label was sent, or the feature vector is generated from the ith label. Okay, so it's not some complicated classifier, but we for this classifier we are able to provide a theorem. So we are able to provide analytical upper bound on its error probability. So why is this important? It is important because we show now that this problem is analytically tractable. Now, this problem was, as I explained, analytically untractable because this distribution is unknown and these elements are dependent. But if we make these elements independent, then we can tackle the problem analytically. At least there is one classifier that we propose. Definitely, there are many other such classifiers which are even much better than this classifier. But for this classifier, we had the following upper bound on the error probability. Okay, so the error probability of this classifier is upper bounded by this. This y is the set from which these features take value. Okay, so the higher, the larger the set, the larger the right-hand side of 1. Here, epsilon is a fixed value. Okay, you can obtain it like this, but it's a fixed value. T is the number of training vectors per label, and n is the length of the feature vector. So if because this is fixed, and because t is fixed and this is fixed, right, in epsilon, if we set n to infinity, 1, the right-hand side of 1 will go to 0. And so it means when we have a feature vector with infinitely many elements, there exists an optimal classifier. Our classifier is optimal. Our classifier is not that good, but yet it is optimal. So this means that definitely there are other classifiers, there exists other classifiers which are also asymptotically optimal. And in fact, even in the non-asymptotic regime, they can provide much better results than what our classifier provides in 1. Okay, so let me show a numerical example. So we have two labels, x1 and x2. The features that this label generates, so x1, the features are generated from these triangular distributions, where y1 is from the narrowest triangle, y2 is from a little bit wider triangle, and so on. But all triangles, they are overlapping. Okay, here for label x2, so x1 is a dog, x2 is a cat. The features are generated from rectangular distributions, and they're overlapping. Okay, y1 is from the narrowest distribution, y2 is wider, and so on. All others are more wider, but they're all overlapping. And this is what is obtained, so the error probability, as a function of the length of the feature vector. Here is feature vector instead of data vector. So blue is the naive Bayes classifier. Yellow is the k nearest neighbor, and red is our classifier. And this is when we have only one training vector per label available. Okay, and here we cannot employ neural networks, because neural networks you cannot train only with one training sample. So that's why we chose KNN and naive Bayes classifier. And here, these two classifiers converge towards 0.5 as n grows, but our classifier decays with a steady slope as n grows, as predicted by the theorem. Okay, now let's put 100 training samples per label. Now, the naive Bayes classifier here, it is much better than, relatively better than our classifier. Why? Because at this point, the naive Bayes classifier for a large number of training vectors, it converges in performance to the maximum likelihood performance. So you cannot beat this classifier. So when the length of the data vector is small, you can consider that the entire channel is almost perfectly estimated. So you know what's the optimal classifier, then is the maximum likelihood classifier. And then that's why the naive Bayes classifier beats our classifier. And then, but as the length of the data vector or the feature vector grows, this converges to 0.5, and our classifier decays with a steady slope. Here, the theoretical upper bound is shown. It is very loose. Sometimes this bound is depends on the parameter r in the Minkowski distance, depends which parameter is chosen. Sometimes it's much more accurate, but what we proved, we use this theoretical upper bound not for having a very tight gap between the real error probability. Instead, we used it to prove that at least one asymptotically optimal classifier exists. So that was the main purpose of the paper. Okay, now we have the similar example for label X1, label X2, but now the features are non-overlapping. So we take the two extremes. We have overlapping features and non-overlapping features. And any other vector, which is comprised of independent and non-identically distributed elements, will have in part a combination between overlapping and non-overlapping marginals. Okay, so that's why we choose these two types of features, overlapping and non-overlapping. Okay, again, here, both classifier T is 1, they converge to 0.5, and this one decays slowly, but with a steady slope that goes towards 0 as the length of the data of the feature vector grows. Okay, so future directions, there are many. Definitely one is, let's confirm this by experiments, which is something that we are trying to do. Next is how can we investigate unsupervised learning. Then can we use knowledge from finite blocklet communications to design machine learning schemes when n is very small? And how can we develop models for reinforcement learning? Can we develop similar communication models for reinforcement learning? And to get more intuition, at least intuition from a communication theory engineer for the problem of the reinforcement learning. Okay, now I will just talk about a work in progress about the blockchain. Okay, so I assume many of you are familiar with smart contracts. Smart contracts are written into the blockchain, but usually smart contracts, they require information from outside of the blockchain. So it's called off-chain data. Now, this off-chain data needs to be verified. The point is, blockchain does not prefer, or the users of blockchain do not prefer centralized verifications, centralized processing, centralized feeding of information. The aim is to make everything decentralized and trustless, so not to trust anyone. So the simplest smart contract that I can explain is some contract that is written on the blockchain that as input requires the temperature, the current temperature in a given city. Okay, then this smart contract asks for the value of this temperature to some device, which in chain link, it is called the aggregator. The aggregator asks for this data from different websites. Okay, those different websites send the data to the aggregator. The aggregator, looking at those values, decides what's the correct temperature, sends it to the smart contract, and based on the temperature that the smart contract sees, the contract is realized or it's not realized, or depends on the specifics in the contracts. Now, how can we assure that the value that is provided, the off-chain value that is provided in this contract is the correct value? So looking at this problem, definitely we can model it as a communications problem, right? We can have, let's say, the smart contract asks for this value, X. This is the true value. Now, X is then sent through these channels, which here they these channels model the websites, and these websites then provide noisy versions to a detector. The detector, looking at those noisy versions, needs to decide what X is. And then the detector sends X hat to the smart contract. And the aim is to minimize the error probability that X is different than X hat. Now, the problem is the detector does not know what are these distributions. Without knowing what are these distributions, how can the detector minimize this error rate? That's the problem that we are currently working on. And that's all from me. Thank you.
Thank you very much. Now it's time for questions. Please, so those who have questions, please use the chat to ask them, or you can unmute yourself and ask the questions in voice.
Hello, can you hear me?
Yeah, I can hear you.
Thank you for your interesting talk. So I had a question about this particular slides where you showed the different distributions, and they were either overlapping and not non-overlapping. So my question was, what is the difference between the two?
Why? We wanted some kind of a model which will take into account all possible feature vectors which have independent non-identically distributed elements, and we came up with that all those feature vectors can take two limits. One limit is overlapping, the other limit is non-overlapping, and that all others take a combinations between overlapping and non-overlapping. So if this algorithm that we showed tends to decay towards zero as n grows, for overlapping and for non-overlapping, it will definitely go towards zero for any combination of overlapping and non-overlapping, which means for any other feature vector with independent non-identically distributed elements. So that was the intention. That's why we chose those.
Is there any reason why the probabilities that are overlapping from your results tend to have a steeper slope than with non-overlapping? Did I get that right from the graph?
Yeah, so can you repeat?
Could you show the next slide? Yeah, so as I can see here, the slope is decreasing at a higher rate than a different graph, yes, with non-overlapping. Do you have any idea why this happens?
Yes, but because it is, at least for our algorithm, it is much more difficult to classify features coming from non-overlapping alphabets. Because imagine we have, because when we have only one training vector available, the information that our classifier will obtain for the channel, it will be very inaccurate. It will be very, the channel will be estimated very poorly. And that's why the performance is very poor. But what we wanted to see whether there is a constant decay towards zero as n grows.
Okay, thank you.
May I have the question? Artem Krasilov speaking.
Yeah.
So my question is more like general. So thank you for this very interesting idea that we have similar problems in the machine learning and in the communication theory. So I very much like that there is a clear dependency between the classification problem in machine learning and decoding problem in the communication theory. So can you provide your general view, what is the benefit of using existing machine learning, how they can be beneficial, for example, for communication theory? So can we somehow utilize the results from machine learning to do better decoding algorithms? So in the reverse direction. What's your opinion on this?
So I'm sure that it works. Definitely, it works. I mean, there's many papers on that, but for me, I didn't want to follow the herd, and I wanted to do the opposite. So that's why I did this. But definitely, it works. I mean, you can see a lot of papers, a lot of claims that it works. My only problem with it is because all those algorithms are based on the trial and error approach. So there is, you play with the neural network, you play with everything until you make it work. And what's the guarantee that if you slightly change something, that it will work again? Usually it doesn't. I mean, you have to, if you change something, then you have to play again until you find again the good parameters or the good, the good neural network that will work on that other communication problem. So, but I may be wrong. Maybe people have found how it works, but for more general problems. But I have my doubts here.
Okay, and maybe following question. So you have provided two examples of this analogy. So can you just maybe list another problems which have similar analogy between the communication theory and the machine learning? So do you have some other analogies? Yeah.
So there was one about I think there was one about secrecy in internet browsing. So there was a very nice modeling that I saw, not from us, from another group, that they modeled how much information one can get from a web browser when that web browser goes through the internet, and they modeled that as a communications problem. So I'm sure that there are, if you think about it, there are also other problems that you can represent as communications problems. At least to me, I thought that this is it is worth thinking about how one can represent problems as communication theory problem, because for me and for our community, this is our strength. If we can represent such problems as communication theory problems, then we can better understand them and maybe solve them. To me, following the machine learning researchers, in their research, in their frameworks, I thought that I will always lag, because they will be always in front in terms of knowledge, in terms of because they have they have accumulated so much intuition. So it's very hard to catch and to catch them and then to beat them in some problems. At least that was my intuition, logic.
Yeah, thank you. That's a really general question. So yeah, thank you.
We also have a question in the chat from Alexei Krishuk. What's norm of difference of empirical distributions?
Euclidean distance.
Euclidean distance.
So it's like using Anderson-Darling statistical criterion, right?
That I'm not familiar with that.
I mean, your classifier looks like you apply a statistical goodness of fit criterion to pairs of distributions, and just select the one for which the criterion value is the highest.
Yes.
And so, yeah, if you use R equal to 2, then it looks like Anderson-Darling, if I remember correctly.
In the numerical examples, we use R equal to 2, and when we play with different R, it gives different performances for different problems. So definitely not R equal 2 is the best for all. But playing with R, we decided not to show different curves for different R.
Okay, thank you. And also a question, usually when working with statistical distributions and like distribution of difference of empirical distributions, I've seen only polynomial error, polynomial dependence of error probability from the length of the words. But you got the exponential one, so it's interesting how you got this bounds.
Well, I mean, at least intuitively, the more independent descriptions that you have of something, the more accurate your classifier should be. And also intuitively, every other independent description of the label carries the same amount, on average, carries the same amount of information about the label. So the ambiguity that you have about the label, it decreases with each new feature on average with the same value, right? So to me, intuitively, it seems that this really holds. The proof is in the paper. Maybe people can look at it and comment on the proof as well if they find some error.
Okay, I'll look into this paper. If this bound really holds, I can apply it to also my own problems.
Yeah, that would be useful for you.
Yeah. Okay. Thank you.
No problem.
Okay. Any other questions?
Yeah, I would like to ask one. Well, my question here is, well, we can see that indeed the algorithm proposed is way superior to the k-nearest neighbors and naive bias in case of huge input feature sizes. And my question is indeed that they are very susceptible to the curse of dimensionality problem. And well, my question is, how would methods that were pretty much conceived to combat this issue, like kernel or ridge regression or SVM, fair in this, would they also exhibit similar behavior, or would they be somewhere in between those, the proposed classifier and the curse of dimensionality?
We haven't tried those algorithms, that I don't know.
Okay.
So maybe I do not believe that our classifier is a very good classifier for this problem. I don't think, I mean, if I compare the performance to assume that the optimal classifier exists, I think that there will be a large gap. I do not know what the optimal classifier is. The aim was to show that at least one optimal classifier exists, and that when you have independent features, you do not have a curse of dimensionality. In fact, you have a blessing, because each independent features reveals what your label is as on average as the same with the same value as the other feature. The curse in dimensionality is also seen in our classifier, and I would like to show this. It is Y here. It is how many values each feature can take. So if the features take values from the real numbers, from any set with infinite number of elements, then 1 is definitely the right hand size of 1 is it's bigger than 1, so it doesn't work. So the curse of dimensionality in our part is in the set Y. It's not in N. It's not in how many features you have. It is in how many values each feature can take.
Oh, I see. Thank you for the answer.
Thank you. We have one more question in the chat from Ruslan Yusupov. Yeah.
So in ICA, in that algorithm, the values are, the length is the same. But in general, the length should be either the same or smaller, right? Because if you have vector with dependent elements, definitely you can shrink it, because the information in those elements is found, a part of the information in those elements is found in other elements as well. So if you try to remove that information, which is found in other elements, definitely you shrink also the length of the vector. It is transferred from non-independent to independent, so from a general case. In that paper, they solve it for a general case, but the algorithm has complexity 2 to the n, so it grows exponentially with n. So it definitely you cannot apply it to a picture, right? Definitely you cannot apply it to something and test it experimentally. If one can design more IC algorithms which are more computationally friendly, that would be great.
Okay, any other questions?
I want to ask one question. And we know that neural networks are used in this task where feature vectors is difficult to extract. And neural networks themselves want to extract features, generate them. And the question is it fair to consider the proposed classifier in the field of problems that classical machine learning techniques cannot cope with, as KNN, naive Bayes, or SRAM, and something?
So I didn't get the question. If you can please repeat it.
The question is it fair to consider the proposed classifier in the field of problems where we can't directly extract features? Or can we make a model like this to those problems?
Intuitively, I wouldn't see why one wouldn't be able to extract features, because you have something as an input to the neural network, right? That what is the input to the neural network you can represent as a vector. That vector definitely inside the elements are dependent. If you use ICA, then you can just transform that vector into another vector, and that other vector is your features or your feature vector. So can you give an example where feature extraction would not be possible?
Oh, okay, I think I better understand your statement.
Okay, thanks.
Okay. Any other questions? So I see no more questions. So thank you very much, Nikola, for giving this very exciting talk. And I think, we have one more question. No, we don't have. Okay, so thank you very much for giving the talk. I hope everyone got something interesting, and really this idea is the idea which you have presented is really very interesting. So yeah, thank you very much.
Thank you for inviting me.
Next time we will next seminar will be held next week, but the time and the topic will be announced a bit later. We may reschedule the seminar one more time, so please check our site and we will send you a message. Thank you very much for participating and have a nice day. Goodbye.
Bye-bye.